Okay, so in this video I'm going to show you some geometric proofs for small angle approximations. So to begin with, we've got this, what I've got here is a sector of a circle, so OPQ, that arc which is the green line. Okay, so that's a sector of a circle. The radius of the circle is this length, which we're going to call lowercase r. OQ and OP are both that radius of the circle, and the sector has got this angle theta. So starting with that, if theta is measured in radians, we can write down the area of sector OPQ is a half r squared theta. Right, that's just a formula for finding sector area in radians. Okay, now if I just draw a straight line, a chord of that circle from Q to P, I've created a triangle here, right? An isosceles triangle with, again, the same lengths OQ and OP. We don't know length of QP, but we do know this angle theta, so that means we can actually work out the area of that triangle. So the area of the triangle OPQ, and that is using what we know about area of a triangle using sine, a half A, which is r, times B, which is r as well, times sine theta, which can also be written as a half r squared sine theta. Okay, and now what I've also drawn is a tangent to that original circle at P. Okay, and I've extended that up to this point R, which is the point at which it joins in a straight line to make a new triangle, a right-angled triangle, OPR. Okay, now this one is a bit more complicated, so what do we need to find out the area of this triangle? Well, we know this length R, we know this angle theta. It's going to be difficult to find out the length OR because we don't know what that is, but we can use sort of simple trigonometry to work out the length PR, okay? Because we know that tan theta equals opposite over adjacent. So opposite is RP, PR, over adjacent, which is the radius there. Okay, so that means that RP equals R tan theta. Okay, so that length is R tan theta, which means we can now write down the area of OPR using our even more simple area of a triangle formula. So a half base times height. Base is R, and the height is R tan theta, which we can simplify to be a half R squared tan theta. Now consider what happens to this triangle as theta gets really, really small. It's going to end up looking something like this. Okay, that's a very small angle. You can see that actually those three areas, you can hardly even tell the difference between the area of the sector and the area of those two triangles. Okay, so when theta is small, approximately we can say that the area of the sector, a half r squared theta, is approximately equal to the area of the triangle OPQ, a half r squared sine theta, and it's also approximately equal to the area of the OPQ, which is a half r squared tan theta. Now, dividing that through by a half r squared, we are left with this very important result. When theta is small, theta is approximately equal to sine theta, and which is approximately equal to tan theta. Okay, so when theta is very small, the way we normally express this is then sine theta is approximately equal to theta and tan theta is approximately equal to theta. That's really useful when we come to try and simplify certain expressions, and also when we come to differentiate trig functions, these results are going to be really important as well. So there's our first two. We've got sine theta is approximately equal to theta and tan theta is approximately equal to theta. Okay, but I hear you ask, what about cos theta? Well, that's going to be a slightly different proof, but there is a small angle approximation for cos theta as well. So to do that one, let's look at this triangle that I've got, well, this diagram that I've got below down here. So this one starts with a sector of the unit circle. So unit circle just means a circle with a radius of 1. So this OPQ here is a sector of a circle radius 1, and the angle there is theta. So we need to start thinking, what other lengths can we work out here? So what I've done here is I've drawn straight down from Q a line to create a right angled triangle within the sector. So last time the right angled triangle was outside the sector, this time the right angled triangle is inside the sector. And then I've also joined up QP exactly the same as I did up there. So let's think about what different lengths we know. So if we've got a right angled triangle, it's easy to work out what the other lengths are. So we know that cos theta will equal adjacent, which is OR, over hypotenuse, which is 1. So that means that OR, that length there, equals cos theta. Okay, you can see now why we picked 1, because it's nice and simple. And we know that sine theta is the opposite over the hypotenuse. So the opposite is QR and over hypotenuse of 1. So that means QR equals sine theta. Okay, and RP, well, we know that OP is the radius 1 of the sector, and OR is cos theta, so RP must just be 1 minus cos theta. Okay, I haven't really got space to write that in there, but that's fine. So we're going to need to use probably Pythagoras to work out PQ, which we can do. By saying, so PQ is the hypotenuse of the triangle RPQ, so PQ squared equals RQ squared, which is sine theta squared, plus 1 minus cos theta squared. And now if we expand that out, we've got PQ squared equals sine squared theta plus 1 minus 2 cos theta plus cos squared theta. And now we should, as soon as we have sine squared and cos squared, we should immediately be spotting, look, we've got sine squared plus cos squared. What does that equal? 1, which is nice. So we've got PQ squared equals 1, that's sine squared and cos squared, plus 1 minus 2 cos theta. So the simplest we can get that really is PQ squared equals 2 minus 2 cos theta. Right, so what can we do with this now? Well, we can actually recognise, going back to this diagram up here, we can see that as theta gets very, very small, that length PQ actually becomes really, really, really close to the length of the arc. So this PQ will be very, very close to the length of the arc. And now remembering that the angle theta is measured in radians, what do we know about the arc length? Well, the arc length, remember, is r theta. So r is just 1, so that means that this length PQ is actually, so the arc length is actually theta. So when theta is small, PQ is approximately equal to the arc length theta. So we're going back to this, we can say theta squared is approximately equal to 2 minus 2 cos theta. Now what we were looking for here is something similar to what we have up here, but for cos. So what we want to do is just make cos the subject of this equation, or make cos theta the subject of this equation. So let's add 2 cos theta to both sides. So we get 2 cos theta plus theta squared approximately equal to 2. Let's subtract theta squared from both sides, so we end up with 2 cos theta approximately equal to 2 minus theta squared. And dividing everything by 2, we end up with cos theta is approximately equal to 1 minus theta squared over 2. And that is the small angle approximation for cos. So these three results are really important. Sine theta is approximately equal to theta, tan theta is approximately equal to theta, and cos theta is approximately equal to 1 minus theta squared over 2, when theta is small.